دونك نبداو ان شاء الله. دونك انا ندوز فيها بركه. بريميرمون الورك شوب هذا سموه ديب ريفورسمنت ليرنينغ ولا بلي بريسيزامون ديب كيو نتورك. ديب كيو نتورك راح نشوفوا ما في هذا الورك شوب ان شاء الله الايديا behind deep queue networks, how it is implemented, and what is the difference between deep queue network and vanilla queue learning. So we have a video here.
We don't tell it how the hand needs to move the cube in order to get there. The particular friction that's on the fingers, how easy it is to turn the faces on the cube, what the gravity, what the weight of the cube is, all of these things it needs to learn by itself. The interesting thing is that kind of...
So as you see, this is an intelligent robot trained using deep reinforcement learning on solving the Rubik's Cube. The robot, of course, is trained not only to solve the Rubik's Cube, but to use his hand in order to solve it. So it's more difficult. It was implemented by OpenAI in October 15, 2019, and it shows how deep reinforcement learning is becoming one of the major domains of deep learning, machine learning nowadays. So before we start, we have quick reminder about queue learning. Maybe Mijda will give us some help here also. Just to catch up before we start talking about deep queue learning. So first, in deep reinforcement learning or in queue learning in general, we learn by experience. This is different from machine learning or supervised learning specifically. Because in supervised learning, we learn by example. So we provide input, which is that data to our deep neural network, and after that, it gives us answer by generalizing the prediction on other data. In reinforcement learning, we don't have any data. It's up to ourselves to build an environment where our agent will train or will learn actually. So in reinforcement learning, we use the word learn instead of train because we don't have any previous data. So we learn by experience. The agent make an experience, learn from it, according to how the environment will respond to it. Second thing is difference between episodic tasks and continuous tasks. In reinforcement learning environments, we have these two type of tasks. We have environments where the task is continuous. It means that it never finish, and like the agent will interact with environment to بلا ما يحبش in Arabic. In episodic task, no. The agent will interact with the environment, and it happens that the agent makes something or make an action that will terminate the episode. So, for example, if we say that we are playing with the Rubik's Cube, if the agent will make the final move that will solve the Rubik's Cube, we end the episode, and we call it an episodic task. Generally, when we are starting now, we may start with playing with episodic task rather than continuous task for simplification. Third point is an action has a reward and results a new state. So like anything in life in general, if we do an action, we have a result, and this result may change the state of our environment. It's the same thing in reinforcement learning, where an agent may make a task or execute a task, which is an action. It will have a reward given by the environment, and it will change the state. If we project this example on our Rubik's Cube, if the agent will move the Rubik's Cube, one of the part of the Rubik's Cube, it will change the state of our Rubik's Cube. And this move, maybe it is a good move or bad move. According to the state, the environment will give it a reward. Let's say, for example, +5 or +6 or even -5. if the action was too bad. So we have another remark, which is the value-based methods try to reach an optimal policy by using a value function. I think that when assisting the workshop of Mejda, she talks about value-based and policy-based training. So in reinforcement learning, our goal is to find an optimal policy to solve something or to do something. We can reach this in value-based method. We reach this optimal policy using a function, which is called value function. And there is also another type of training, which is policy-based training, where we don't try to find a function, but we go directly to the optimal policy. For now, we are interested in finding a function that will be guiding us to find the optimal policy. But how? The second point is this function of an optimal policy maximizes the expected return G. So if we are being pragmatic, the best policy will give us the best accumulative return G, which is the sum of each reward on each task. This is intuitively, in fact. If we find a function that can give us the proper action that will, at the end, maximize our cumulative reward, it means that our Q function is rightly directing us to the optimal policy. Third point is, as a reminder, is epsilon greedy policies solve the exploration and exploitation problem. This is a common problem in reinforcement learning or in general, not just deep reinforcement learning, where we have a problem with exploration and exploitation. What we mean about exploration is that our agent must explore new actions, even if he knows the best action based on his previous learning. And for exploitation, he must exploit his training in order to choose an action. If we can simplify this concept, let's project it on a human being. Let's say, for example, I was learning something during 5 years. I experienced it, I learned a lot from it, so I can have basic knowledge about it. After 5 years, I tend to do actions that match with my previous actions in the past 5 years. Donc, in Arabic, I tend I tend to not take a risk to try new actions because I had learned a lot during the 5 past years. This is the same thing in reinforcement learning. So an agent that is trained for a given time, generally tend to not to try new actions. This is an exploration problem. And the contrary, if I was learning something during 5 years, and at each step, I do something that is not based on any previous knowledge, I have an exploitation problem. So I'm not exploiting my previous knowledge or previous data in the case of reinforcement learning agent. This is also a common problem. What we do generally to solve this problem is to use an epsilon greedy policy, which means at every step, I flip a coin, for example. I give 0.8 chance to take the maximum value of the action that give me the optimal reward, the maximum reward, and 0.2 probability to take a random action. So at each step, I flip a coin and I see if I need to take the optimal action based on my knowledge or take a random action. This probability will increase by time. So if when I start with 0.2 probability to take my trusted action that I gave it the maximum reward. So because I don't have prior knowledge, and by time when the agent is learning, I tend to increase the probability to trust my previous experience. So after seeing brief reminder about Q-learning, I invite you to watch the workshop of Mejda, which is recorded. If you tend to find this a bit difficult about the remarks. One of the limitations of Q-learning nowadays is it's not practical with environments with large or infinite state or action space. Like you saw on the previous workshop, the Q-learning is based on a Q table where we have the state and action combination. So in the rows, we have the state, and in the columns, we have the action. And each state action cross, we have the value of taking that action in that state. This is problematic actually, because in environments with complicated state, like you see here, games where we have an image of, let's say, 200 by 400 pixel. For stock markets, for example, we have many two features of our state. And for robotics, for example, for robots, we have gravity, pressure, temperature, very other features that are hard to index in a table. And even if we manage to index those state, the size of the table is non-practical at all. We can store it, we can use it, we can't use it, and this is not practical to use it nowadays, because most of the machine learning or deep reinforcement learning models are stored with limited constraints like space or memory or other hardware limitation. But fortunately, modern problems, like he said, require modern solutions. In fact, in 2015, a group called DeepMinds, which was acquired by Google for $400 million, had published a paper called Deep Q Networks, which tend to train agent on playing Atari games, which is a set of games of about 500 games or simple games actually, to get the best score. But what are we going to do is not read the paper, but solve this problem with our answers. So we followed the same path that the DeepMinds group had followed, by questioning our current method and trying to make improvements using deep learning. So actually here we have an interactive course. If someone tend to ask a question or give a remark, that would be appreciated, because I will be asking you a question, not giving you answer. So figure out by yourself. The first question is how to replace the Q table. We have problem here. We need to replace the Q table, but using neural networks. We tend to know by this series of workshops that neural networks can be trained to fit on linear or non-linear function generally. So how we can use neural network in our problem to eliminate the Q table? Anyone with answer? So I'm sharing the screen. I can see the Hangout. Let me check if someone has an answer. You can open the microphone if you want. Abdurrauf. You can talk, because when I'm presenting, I can't see the messages actually. You'll do me a favor. Anyone with answer? Okay, Abdurrauf said, by finding similarities between states. How actually? Do you have any explanation? Okay, that's a bit what we are going to do. Let's say here. So we tend to replace the Q value function with a deep neural network that will fit on this function. It means that this neural network will be the source of our Q values. But how this deep Q network, what is the shape of this deep Q neural network? The output layer holds the Q value of each possible action. So we suggest that we make the action space discrete. This is the case of the Q-learning paper, deep Q-learning paper. The discrete action space, it means that we have a limited number of actions. Let's say go left, go up, go right, go down. So the output of our deep neural networks is the Q value of each action. The input layer. The best thing about deep Q networks is that the input layer takes the desired representation of the state. What we discussed earlier, that it is difficult to extract features that it is indexable from complicated state. In deep neural network, it is the contrary. We tend to use a pipeline on convolutions or dense layer, for example, or a sequence of LSTM or RNN cells in order to represent our state. So these input layers will be the representation of our state. We don't take how or which is or how it will be represented. It is for the input layer to do it. For example, for convolutions, our state will be a set of features that will be flattened and passed to our neural network, like you said, you saw with the CNN workshop. We can have a dense layer for simple representation, for example. We can have also an LSTM, for example, for sequence data in the case of market or for business data, where we tend to use LSTM or RNN to predict sequence. So as an input, we have our state, environment state, which can be anything, in fact. And at the output, we have our desired Q values, which is the same as a function. So all clear, I think. We move to the second point. So here, as a representation, here we had a state and an action, state-action combination, and the Q value. Here, no, we have the state as an input, we have deep neural network, and as an output, we have the Q value of each action. As simple as that. The question now is how to optimize our model to give us a correct Q value of each action based on state. Let's start. The agent took an action A in state S. This is the case in the Q. The agent moved to the next state S prime and received a reward, R. So this is a very simple case. We have also a discount rate gamma that reflects how much we care about the future reward. This is actually related to the Billman equation that was presented in the Q-learning workshop. So if we have a gamma that it is close to 1, we care too much about the future reward. And if we have a gamma that is close to 0, we care so much about the immediate reward. This is something simple that you can catch up with viewing the previous workshop. So here we have the equation, the famous equation of updating the Q value of a state-action combination. Here we have the Q prime SA. It means that the new value of SA state and action A. How we get it? We get it from adding a constant alpha, which is the learning rate actually in machine learning, and the immediate reward turned by the environment plus gamma multiplied by the maximum Q value that was given by, that is extracted from passing the new state to the table and get the Q value. So here we have the estimated return value, like the accumulative reward starting from our from this action, from action A, minus the Q value that of SA. This is a very famous equation. So here, if you are familiar with machine learning, this is ways in order to similar to the way we update the weights or the parameters in supervised learning. So we have a new value that we get it from the new value plus the learning rate multiplied by a quantity of something, let's say, for simplification reason. So if you tend to witness something here, a good Q value for an action A given state S is a good approximation to the expected discounted cumulative reward. We mean by this that this quantity tend to be equal to this quantity. When does this happen, this will be zero, will be near to zero. So the new value of Q will be the same actually. So in order to fit our table or our deep neural networks, what our purpose is to make this equal to this. Let's say equal, but it's not near equal, but not equal. So this is our goal, to make the current Q value, which is QSA, nearly equal to the expected reward, which is the immediate reward plus gamma multiplied by the maximum of the Q value of next state. This is our goal. So we have two parts to make them catch up with each other. How we can do this? Let's see this diagram. We have state here, and we have Q networks. We have our deep neural networks that we are willing to fit to our function. We have the Q values, all the Q values. Let's say we have 4 Q values. Then we select an action that turns to be the maximum, the action with the maximum Q, the highest Q value. We have an action. We make this action. Our environment will give us a new state and the reward of this action. What we do next, like you see here, the maximum value of the next state. So we give this state to our Q networks, the same Q networks. We extract the Q value of the highest Q value, and we add it to our reward. As simple as that. And we get this part. So this part is now checked in our hand. We need to get the second part. How we can get it? It's simple. We get the Q value that we get earlier, like you see here. The Q value of S A prime. It's the Q value actually of each one here. Like each Q value here, we can get it and use it. So we have two parts here that are estimated by our deep Q networks. So we have a forward pass, two forward pass on our Q networks. We just use a loss optimizer. We pass the first and the second parameter, part, and the loss optimizer we tend to tune the parameters, which is in fact the same parameters used here are used here. So we pass these parameters to the loss optimizer, and it will tune the parameters in order to make these two values catch up with each other at each iteration. So we have our new network weights. But here actually we have a problem. Can someone, so here we have like we said earlier, can someone explain me this problem? We are chasing a moving target. So here we are chasing a moving target. How we are trampling in this error? By using it. Hello?
Hello.
So here we are chasing a moving target. Why we are having this error?
Why we are having
this error, this trap, where we are tend to trap to this error?
Je pense que le problème, c'est qu'on ne pourra jamais converger ainsi. C'est pas ça.
Exactement. Exactement. How? Because if you see here, if we can see here, let's say this carrot is this value, the reward plus gamma multiplied by the maximum of q, and this is the q value of SA. If each time we are trying to match this animal, let's say, don't say donkey, this animal to this carrot, each time the donkey move, the one how the carrot move with it. So each time we change the parameter here, and we change the parameter here. This change and this change. So we are going on the same direction. There is no thing that can get closer to the other thing, if we can say. We call this moving target. How we can solve this is by separating this guy from this animal or this donkey. So we put the carrot aside here, which is the reward plus the gamma for the highest q value of the next state, and we put the donkey here, which is the QSA value. When we do the optimization here, maybe we move the donkey here. So we do optimization according to the animal, not according to the carrot. We move the animal, and we move the carrot slightly a bit, not that much, but slight a bit. And then maybe we move the carrot more closer. We move it closer to the animal. So how we can do this is by using what we say the T target. The T target. So we will use local neural network and the target network, which is two separate networks with different weights. So when optimizing one of this network, the other network will not change. So if it means that when we move one of these parts, the other one will not move on the same direction of the other. How we can do this is that the target neural network gets slightly updated based on the local neural network weights. So the target neural networks, which happen to be our carrot, will get updated, slightly updated. What we say soft update, it's a formula also, based on the updates that are happening to the local network, which will get optimized by our optimizer. So the local network predict the Q values for the current state, and the target network predict the Q values for the next state. Because if you see here, the carrot is predict the Q value of the next state and add it to the immediate reward. So our target network will predict the Q value of our next state based on the action of the local network. So if we try to modify our last diagram, here we have the same part as the first one. In the second part, instead of passing the new state, which is happen to be here, to our local network, no, we pass it to the target network, and we add it. We get the result from the result added to the immediate reward in order to get this element. So instead of passing it here, we pass it to another network, which happened to be called target network, and we get our Q value here from the previous pass. We make the optimization according to the parameters of this network, which is the local network. So the local network will get optimized, then the target network will be updated, slightly updated by changing fixed percentage of its parameters, not all of its parameters. So someone to answer this question, please. In supervised learning, why we shuffle the data set to give why the shuffling the data set give us the best accuracy? This is a common question in the machine learning or supervised machine learning. Anyone with an answer, please?
pour éviter la corrélation entre,
Yes, because
les
for
données.
example, if we have yes, because for example, if we have data set of dogs and cats,
SD, on n'entend rien.
and now, okay, now is it okay now? Okay. So in supervised learning, if we don't shuffle the data, we may have a poor convergence because the network will be working on a cat's data and suddenly it will shift to dog's data. We may have very slow convergence. It's the same thing with reinforcement learning because at each step of our experience, we are passing the state. We get a new state, and in the second step, we pass this new state to our local network. Like this new state will be the state here at the next iteration. This will lead to very correlated state. So we tend to have a poor agent that is learning from its environment. In our case here, like he said, in our case, we are having big correlation between consecutive states, which may lead to inefficient learning. How we can solve this? By using what we call experience reply. Experience reply is using a buffer with a given size in order to store the experience at each iteration. Let's say our buffer has a size of 5. So we tend to store 5 experience in this buffer. And when the buffer is full, let's say the 5 experience are stored, we get a batch size of 3 items or 2 items to make the back propagation with and optimize our network. So we don't call this loss optimizer at each step. We call it when we reach a certain number of steps only. And how we can break this correlation is by by making the choice of these experiences random. So, for example, if we have a buffer with 60 experience size, we get 30 experience, we to make this 30 experience random. في لو كا هذا ما يكونوش les expériences هذو consécutives. So we are breaking the correlation between state. It's a small update to our deep Q networks, but it will give us much better convergence. So if we talk a lot in theoretically, we try to build DQL agent that will solve a given problem. I don't know if you have the link to you have the link to the Colab. I may share it with you here. Let's say it is available also in the GitHub repository of the event. You may use it. So you seeing are you seeing the code or not? Just someone to answer me, please. Can anyone see the code here? Or not yet? Hello? Are you hearing me? So can you see the code when I switch to the next tab? Okay. So here we have Colab, which will be trained to solve an environment called Cartpool. So here we have OpenAI, which give us set of large set of environments. Let's say here, if we tend to try some example. For example, we have the Atari game that we talked about earlier. It's a very large set of environments. We have also here robotics, if you want to try with robotics. So all these environments are normalized and have their own states, representation, and action representation. So you tend just to get the input and the output into and from the environment, and also everything is ready for you. So in our case, we will tend to build a reinforcement learning agent that will play this game called the card pool. So like you see here, a pole is attached by an actuated joint to a card, which move along frictionless track. So we have here a pole and a card. We tend to go right and left to keep the pole standing. So if you want to see the actions and the state, we go here, for example, to GitHub repository. We have here the observation 0, 1, 2, 3. Like in the first one, we have for the first one we have the card position according to environment, the card velocity, and the pole angle and the pole velocity output. Actually, I don't give too much importance to this input in our example now. The most important thing is the actions. So the 0, for example, we have push the card to the left, and the 1 is push the card to the right. And also an important thing to observe is when the episode is terminated. Like here, episode termination, pole angle is more than 20 degrees. Like if the pole gets to 12 degrees, sorry, the episode is terminated. And if the card position is more than 2.4 to the left or to the right, it means that we shift largely to the left or the right. And the episode length is greater than 200. So we don't go over 200 episode. So here, by default, the Colab environment doesn't render the video you saw earlier. So we run some code that it was implemented for you in order to set up Colab with OpenAI Gym. So we run it here. Meanwhile, does anyone have a question? If we can answer it now. Okay. So we import some helper functions. If you want to try it, just execute the code. So don't need to modify it. Here we start building our DQN agent. So here we import some. We are using PyTorch actually in order to build our networks. So here we make some imports. Here we are defining the class of our neural network, which is shared by. It is the same neural network for our target and local network. If you can see with me here, as an input so we are defining the input and the output layer of our networks dynamically, setting the state size and the action size. So here we have the action size and the state size as the input. We have also here the hidden layer, the number of units in the hidden layer, and the two hidden layers. So at the beginning, we set the first fully connected layer. We are using the fully connected layer because our state representation is very simple, like you saw earlier, not an image or a sequence. So we just use a fully connected layer, which is here linear or dense layer in TensorFlow. So we have as an input the state size, and here as in labels the number of the fully connected next layer, which is FC1 units. So here we have the analytics. For example, here we have state size FC1 units, FC1 units, FC2 units. It's a common thing to do in PyTorch. So you just switch between the parameters in order to make the network comprehensive. So we are defining here our hidden layers. Here we are doing this, the forward pass as simple as it is, using the ruler function and the forward pass of each layer. And we are returning the value of our last layer, which happened to be the FC3 layer, with the action size as an output. So here we have two output for our case. So it's simple neural network class like you tend to define it in supervised learning. Here, actually, we are defining some hyperparameters for our agent. Like you see here, the buffer size. This is big buffer size, actually, because the number of episodes are quite high. So we have here the reply buffer size, the batch size. So from, let's say here, I think here is 100,000. We get 64 experience. So like you see here, the randomness of choice here is very, let's say the proper word, which is if we can say is not biased. So we are from 100,000 experience, we are getting 64. So the chance to get two correlated experience is very low. Here we have gamma, which is 0.99. So we give a lot of importance to the upcoming states. We have here what we call the TAU, which is a hyperparameter that we will talk about it next. Don't forget about it now. We have the learning rate, which is the constant alpha, like you saw earlier, but here we are using it in our optimizer. And update every, let's say here we are using 4. We can use, for example, we can use the same as the buffer size. So we tend to not repeat some experience, but we can use 4, for example. Let's say for every 4 step, get 64 experience. In the first episode, we tend to not get 64, but we get 4 experience, but it's not bad. By time, we will get 64 non-correlated experience. Here we are setting the device, if CPU or GPU. It's preferable to use the GPU instead of the CPU to faster learning time. And here we are getting to the most important class in our reinforcement learning, which is the agent. So in the agent, we have 4 methods, which is the constructor, step, how we take step in our episode. Act. An act is used when the agent is trained. So after we train the agent, we use this to make actions. It's like predict in supervised learning. We have here learn. So how the agent will learn, and we have here the what we talk about, which is the soft update to the target network. So we go through it step by step. So first, we init the state size and the action size of our environment. Here, as we give it to it as an input. We set a random seed in order to initialize the parameters of our network. And here we define our two networks, the Q network local and the Q network target, using the same signature, actually, the state size and the action size. But here, when we use the optimizer, we pass only the parameters of the local network and the learning rate. So we forgot about this one now. This one we will be updated based on this one. And the optimizer tend to only optimize the local network. The self memory, which is our buffer, we set it according to the class that is called reply buffer. Here, the reply buffer is class that I am defining it here, but it's not important to talk about it. It's that, just imagine that it's a reply buffer where we store our experience. That's the most important. After that, you can implement it using any data structure you want. Here we init the number of steps. We tend to be 0 for the moment. So at each step, in order to make a step, we give our agent the actual state, the action, the reward, and the next state given by the environment. The agent will store this experience in the buffer to get to it after. So increment the number of steps, and if the number of steps is equal to the update every variable, we start the training, or we start the learning, So what we do here, if length of self.memory is bigger than the bot size, so if we can, for example, like we said earlier, we can forget about this condition, or we can use it actually. If the self.memory is length of our memory is bigger than batch size, so we can learn. We can get more. We can get 64 example, not only 4 example. We can get yes, like I said now. So we get our samples from the reply buffer randomly, and we start the learning process. How we learn? So we have a bunch of experience. We have a list of experience, and we have gamma. Gamma, which is how much we value the future reward. So we get the state and the action and the reward and the next state from each experience using the spread operator in Python, like we may say. Here, what we do is that in the target network, we compute the Q value of the next state, like you see here. We pass the next state, and we get the maximum Q value using this operator here. So don't exhaust yourself with going over each method. Just understand the line. Here we are getting the highest Q value in our target network based on the next state. So the Q target is the reward plus gamma multiplied by the Q value of the highest Q value of the next state. This element is what we are going to pass to our optimizer also as a target. So like we saw earlier in the diagram. Here we have the Q expected, which is the Q value, the Q values returned by our local network. Like we see here, we pass the states to our local network and we get the Q values. So here we tend to pass these two elements to the loss of mean squared error loss optimizer. We get the loss, we make the back propagation, and we optimize our parameters. So here we are optimizing the parameters of this network, the local network. But like we said, when optimizing the parameters of this network, we slightly update the parameters of the target network. How we do that is by using soft updates. How soft update works? It's by this formula. The theta target will be given the value of this, like we say in French, tau, multiplied by theta local plus 1 minus tau multiplied by theta target. So the TAU element variable here is our famous tau. So here we get in the soft update, for each parameter in the target network, we get its match from the local network. And how we update it? By using this formula. So we keep a percentage of the current parameter, and we change percentage using the local network parameter, like you see here. So we are slightly updating our local our target network parameter weights, like we saw earlier. So in general, this is the class definition of the agent class. And now we have another important function actually, which is the DQN function. So after defining the agent, we must define the DQN function, which will interact with both the environment and the agent. How we do that is by first giving it this parameters: number of episode, the maximum number of time space per episode, which is the steps per episode, the epsilon of the start, which is 1, and the epsilon of the end, which is 0.01, and the epsilon decay, which is 0.995. So these three parameters are. So the start, when we start our train learning, we tend to not trust our agent. So we maximize the exploration rate. And by time, we minimize the exploration rate using the epsilon decay. At each time, we subtract 0.995 from the actual epsilon till we get to the 0.01, and we keep it stable for learning purposes. So we have here the list of scores, the score window, which is, for example, here we get the last 100 score to display it. The epsilon of start, which is epsilon start, and for each episode in number of episodes that we are willing to train on, which is in supervised learning, like we say, the number of epoch. We have the state, the initial state, given by our environment. Like here we have the env.reset. We will talk about the environment later. We have the initial score, which is 0. And for each step, what we do, we make an action, agent.act state episode. So when we say agent.act, it will act randomly because the network is not trained yet. So based on the neural network, our neural network, it will act. If we can see the act method here, it's a simple one. Just make a forward pass, and at the end, if make a flip a coin, if the random number is higher than epsilon, give me the maximum, the highest Q value. Otherwise, give me a random Q value. So it's very simple function. So after making the action of by the agent, we give this action to our environment when env.step action. After calling this method, the environment will give us the next state, the reward, and if the episode is terminated or not. So we start the experiments like you see here. We iterate to the next state by giving the state our next state. We update the score by adding the reward. And if the episode is done, we break the loop operation. So here, at each end of an episode, update our learning. We update our epsilon, and we append the score to our score windows. So here, if you can see, the next epsilon is the maximum between epsilon end, which is 0.01, and the epsilon decay value, which is epsilon decay multiplied by epsilon. So here we are decreasing the epsilon. And we print some information. So if you can see here, everything is happening inside this class, which is the agent class. So the learning is launched automatically after doing the step. The number of steps is equal to the update rate. We make the training. Otherwise, we don't do anything. We just store the experiences. So this class is very important in one training agent. This one actually is common between all the most of the DQN algorithms. So here, if we want to run to play a bit with our agent, so first, when you train your reinforcement learning agent, one of the key things to do is to watch a non-trained reinforcement learning agent. So, for example, if a non-trained reinforcement learning agent makes score of 5 in each episode, your trained reinforcement learning agent must beat it. So, first you must watch non-trained agent. What we be doing here. So here we are initializing our agent based on the state size of the act size of our environment, like you see here. env.observation_space.shape and env action space. So here we have 200 episode. That's 200 step in one episode that we will watch. So here we are just acting and making step without any learning. May take some time. Like you see here, we have we have an episode of 9 steps. So after the ninth step, the episode was terminated because the agent failed. Like we said earlier, this environment we succeed when we go over 200 step. Here we are getting to nearly 10 step, and we finish our episode. So if you train your network, we must have better number of steps than 10. Like you see here, we are training here. The average score of each episode is going up. We start by 17. We tend to go lower a bit, but we will go up soon. Like you see here, 58, 59, 63. We may reach 200 because we have a number of I think 1,000 episodes. Where we are defining this. Yes, 2,000 episode with a maximum number of 1,000 steps. Here we will not reach 1,000 because the maximum is 200. So we have 2000 episodes with maximum of 200 steps per episode. So it may take time. Meanwhile, is there any question? Well, is there any question about the code or something that is not clear? Okay. So it may take some time here. أكم صايمين بالك. Okay. He said crystal clear. So if there are any questions, just leave it here or feel free to ask. I know it's a bit difficult to follow the code when someone is not having much food during the morning, including me, but it's okay. So here, meanwhile we are waiting to our agent. Let's see how we can how we can experience with the learning agent. So here, if you can see this one here, I don't know if so when training an agent using the DQN function, if the score window, the average score, go beyond 200 unit, we break training and we save our network. Here, and because we tend to have with more episode, it doesn't mean that we will have a better reward with each new episode. No, your environment may work well in 100 episode, and after the 100 episode, things go wrong and the rewards start decreasing. So it's up to you to experience your environment and see which is the best reward to do it, to stop the environment at it. So here we are using pre-built environment. For example, if you are working on some project, you tend to build your own environment, like using the OpenAI interface. OpenAI interface, which is these functions. So if you are building your environment must include these functions: the function act, the function step, the function reset, and the function render, and the init, and the constructor. So we generally, when playing with reinforcement learning, we use the OpenAI environment. But when using real case scenarios in project or something, you tend to build your own. Don't know if the training has finished. Not yet. So if we can go to here. Something I want to stress on is this one. Difference between this one and this. Here we are passing the new state to the same neural network, and then getting the output and adding to the reward. Here now, if you see here, we are passing the new state to a new network and then adding the reward. This is the main key in understanding the deep neural network, deep Q-learning paper. So we are using a different set of weights to get this element. Another key thing is this one. These are the two main parts that took me time to deal with. The moving target. When we are optimizing two sets of weight at one time, like we are doing here, we are moving the two weights at the same time. So no one will go closer to the other one. In order to break this problem, we separate the two parts. We give this one its own network and this one its own network also. and we update this one according to this one using the soft update function. I think that we are close to finish here. So we didn't reach the score of 200. We may use the same the same agent without stalling the network. Ah, but it's not different. It's not problem. So we here, if we tend to not plug the weights, if you can see here, we have 200 steps. Actually, our network is doing very well, because at this episode it reaches 200 step with a reward of 1. So actually it's not the reward of 1, but I'm not printing the total reward. So let's see here. It's a reward of 200 in 200 steps. So our agent is performing very well. So I think that this is the end of our code here, and we tend to end our workshop here. We have one slide I didn't show you. صحفتكم. So if there are any question I may answer, I am very happy to receive it now. Is there any question? So before we end, if anyone can send a message here as a sign that everything is clear, okay or not okay. صحفتك ناس. بلمسني. So يعطيكم الصحة، وإن شاء الله هنتلاقوا دوتر اوكازيون إن شاء الله. برافو قاسم، مش قال لي ميرسي بلا جميع. So thank you. بقاو على خير والسلام عليكم. باي باي. هيا سلام.